We'll go ahead and leave the door open because I imagine some people will probably drift in, and let's go ahead and get started. Now, there's a ton of stuff that I want to cover here, and so I'm going to move pretty quick, and then there'll be an opportunity at the end. I'll stick around if anyone wants to ask me additional questions, and if by chance I talk too fast and we get done a little early, then great, I'll be able to expound on some more topics. But okay, so what we're going to cover here is fog computing, specifically Eclipse IO Fog, although fog computing in general to an extent, and IoT solution architecture. And so just so you know that there's some credibility behind this, who am I? I spent a year advising the city of San Francisco on all things IoT, and that resulted in the emergence of a fog computing layer, which is something I'll describe to you in this talk here. I've been programming since I was 8 years old, and I'm originally from Chicago, and I escaped the cold, and now I live in the San Francisco Bay Area. And I'm currently serving also as IoT Program Director for Northeastern University. So we teach IoT, and we just want the world to be full of IoT talented people. So I'm also founder and CEO of a company called IoTrax, and IoTrax makes open source fog computing, and our whole goal is to make it possible to run software in any given physical space around the globe and be able to securely and remotely administer that software. And so the result of it is that we have created a project called Eclipse IO Fog, and it's part of Eclipse IoT. And so you can use it now. It's fully distributed, which means that, typical for Eclipse, it's an Eclipse public license, and you can use it commercially, and you can put it on your own infrastructure. So that's quite different than a lot of IoT infrastructure, which usually involves some proprietary cloud. And what we're going to talk about here is we're going to do an overview of IoT, the purpose of which is to set the stage for our discussion about the challenges of IoT solution architecture. We're going to look at some common architecture that's taking place today, the reasons for having fog computing, and then what is the emerging patterns in enterprise IoT architecture. So let's get right down to it and talk about defining IoT succinctly. This is what I used to say. And it's kind of close, right, that everything in the world is interconnected, can share data and instructions and so on. But there's a lot of misconceptions that need to be cleared. So one misconception about IoT is that it's all new. This is the greenfield assumption. And in anything other than consumer products, this is absolutely not true. So you've got to get past that if you're going to properly frame up IoT. It's not about mobile apps. Oh, well, that's really unstable. It's not about mobile apps and wearables, even though that's a component. In a way, our smartphones were the original fog computing that enabled wearable technology to come to the rise. And it's not just about smart homes. That's only one component. And it's not just about predictive maintenance. It's not just about smart cities. And it's certainly not just about data. The instructions that are given to the physical devices and the actuators and so on is just as important as the data that the sensors and things generate. And it's not just about the sensors, and it's not just about connectivity. You can have the world's best wireless network that costs nothing and reaches every single square inch of the planet, and you still don't have an Internet of Things. You have an extended internet. You are missing a lot of the pieces to connect the things. So the reality is, it's all of these things and so much more. And so what I tend to say now is that it's really about extending the internet to a greater range of much larger set of digital devices and systems, things that don't necessarily have screens and keyboards and so on. And the question is this really a useful definition? No, because you can say that to somebody and it still doesn't answer any of their questions. We're just simply too early in the Internet of Things to try to be concise, but we do have a lot of misconceptions starting to brew that usually need to be brought up. Brief history, breeze through this because this is not that important for this talk, but we're coming out of M2M. And so as a show of hands, anyone familiar with machine-to-machine, M2M? Have you worked in M2M? Okay. Cool. Yeah, and we've been doing this for 30, 40 years, right? So this is not all that new. Thing is, what we're coming out of in M2M is closed-loop systems on private networks that are incredibly fast. They use real-time operating systems, and operational technology has been really the business driver of having all of this. You've got stuff like embedded software and SCADA networks. And we also have over 1,500 protocols. So anyone who thinks that IoT is about settling the protocol debate, this has never been the case, and we've gone for many decades in M2M and never settled any kind of protocol debate. So it's not likely that a single protocol is in any way going to help us. So yeah, it came from the 70s, and it's about 75 billion right now as a market size. We're talking about trillions of dollars of impact of IoT within the next 10 years. Are we really going to reach that? I mean, we might, right? It might be the time for the breakthrough, but we're not coming out of M to M at 1 trillion and going to 4 trillion. We're not really that close at all to what we're talking about for IoT predictions. But as the two plates collide, it's really the internet colliding with M to M. And so here's what's enabling the transition. We have new types of connectivity, more connectivity than we've ever had before. And we have dramatically lower or dropping hardware costs. And so, in fact, commodity computing hardware is just so cheap, I don't know why you would build a board yourself anymore, although there are cases. And very important, we have new battery technology. So to go from M to IoT, you have connectivity, and then you have these great batteries to power it. Well, we're not where we want to be yet, but we're good enough that we can do deploys. And for the first time ever, we have what I would call standardized data science. We've always had data science, but these were very elite folks that probably sat in a back room and really only managed very large-scale problems for a conglomerate or a large corporate. Now we have data science taking place in all circumstances, and it's actually kind of a skill set that most people are tacking on to their existing engineering. We have cheap sensors. MEMS is a great example. We had vibration sensors in the past that cost hundreds of dollars at a minimum, and now we have vibration sensors that are MEMS-based that cost dollars. So it's awesome time. And we have economic incentives that have emerged. It's never been so expensive to employ people to do processes that could be automated. We just don't live in a world anymore where you can say, well, if I hire 20, 30 more people, we could just keep that thing running. You have to look at ways of automating, and you need data in order to do that. And there's just a lot of incentives to cut down on the human labor there. So the origin is we've been looking at the term Internet of Things since '85, and we've tried many times to bring this about, but I think the reason that we're finally actually succeeding is because of some of those things that I mentioned with regard to connectivity and the cost of things. So what we're doing to a great extent is we're looking to consortia to try to solve this for us, which is good. I mean, there's an impact there. But it's not going to produce any kind of a prescriptive architecture that's one and done. And so, here's some of the consortia that some of them I work with. I work with the IIC and, of course, Eclipse IoT. And, they're going to break new ground. They're going to provide security specifications that can be useful and so on. But we can't consider them the solving entity, right? The IEEE takes forever. Usually when they do solve something, it works, but it takes a long time. And so let's take a look at the drivers behind building the Internet of Things so that we can get a frame up for what we might want to architect. One of the primary ones from a business perspective is cost reduction. If you get the right data, you might be able to make greater utilization out of the tools that you have, out of the machinery and so on. Enhance customer experience. So in a way, you want to be the best-selling television set or the best-selling refrigerator, the best-selling automobile. And IoT can help you get there. And we're looking for greater efficiencies. Just in general, data about the flow of operations is going to give some opportunities to save 5, 10%. And really important these days is we're also looking for waste reduction. So first you have to measure, and then you can start to make improvements. When it comes to things like saving lives or improving safety and so on, we actually are looking for this technology to help us produce greater outcomes. And we're looking to do better science through better measurement and so on, and avoiding losses and catastrophes. And there was one really good example of this is in the oil and gas industry. If you have a breakdown on an oil pump, there are certain types of breakdowns that cost several $100,000, and that's in the labor and the parts, and you have outage of that pump for a while. And often, to prevent it, you just needed to spend a couple of $1,000s doing some routine maintenance, but you're not sure which pumps deserve it. And you can't do it to all of them because then you'd be paying as much as the loss. So just preventing that breaking moment of downtime or catastrophic failure is good. And it's controversial, but we are actually looking to automate and eliminate what you would call kind of routine efforts in business. So right now, adopting IoT is very hard. there are very few companies that have an easy time of doing it. Maybe the ones that have been pioneering already for the last 20 years have it easy, but there are some key reasons to be doing it, and we're looking to build a competitive advantage in the companies that'll last maybe 5 years or so. I mentioned the efficiencies, I've mentioned the cost reduction, and also a lot of companies are pursuing IoT already and implementing IoT infrastructure because today it's a competitive advantage, and in a short number of years it's just going to be table stakes. So if you don't get out there ahead of it now, you'll be the company that is left behind, and you'll be copying everyone else instead of having any kind of a IoT infrastructure inside your company. So, but let's look at the technical perspective of why we're doing this. You could argue that we're doing it just because we can. We tend to do, as a species, we tend to do things like that. But really, technologically, the Internet of Things is about finally getting our computer interaction with reality. We've been talking about it for a long time, and it's in science fiction and everything, and now it's finally coming to fruition. Different type of automation. We're looking to have eliminate errors. We're looking to have precise measurement in daily processes and things so that we just in general improve outcomes, improve the world. And we're looking for new sources of data. There are things that we've always wanted to measure, but we lack the ability to measure them because of cost or because the benefits just weren't worthwhile, and now if it's super cheap we can do it. And we're looking to gather vast quantities of data so that we can do better science, really. And this is my favorite one. Ultimately, we're also extending the human-computer interface to include devices and things that are completely unrelated to our past HCI. So keyboards, touch screens, mice, these are all going to stay in place. But eventually here, we'll be able to wave our hands in the middle of a room, and if we make the right gesture, we'll lower the lights. Or in a workplace, when somebody makes the gesture that means they need help, the assembly line will automatically stop, so that if they're in a position where they can't safely reach the pull cord, they're able to still stop things. So, and from an industry-wide perspective, we are so far from this, but we're looking for a dynamic interconnection across all business systems, and it has to be secure, it has to be kept private when needed, and so on. I have no idea how we're going to do it. We've tried with electronic data interchange, and we've done a fairly good job of mixing some systems, but ultimately, the true Internet of Things has everything connectable to everything if permissions are granted. And we're looking for a large common talent pool, and we're looking for standardized security models. This one's especially tough. I'm doing a lot of work in this area, so I'm happy to talk about it outside of this presentation, of what's being done and what I think is going to be successful. And ultimately, also, we're looking for the low unit costs that come from finally arriving at some standards. Why can't we do it yet? Connectivity is good, but we are still really far away from having the type of connectivity we need in all places. Speaking again of oil and gas, there's a lot of satellite connectivity being paid for, and satellite, although it provides a private connection, it's not actually that reliable sometimes because of fog rolling into a low-lying area and so on. And you're just not going to put a bunch of cell towers out into the Sahara Desert because the only customer is the company that's asking for it. So how do you manage this connectivity? There's a big lack of talent. I think that's one reason why you're all here in this room, is because this is an interesting area for you. And we still don't have the types of batteries that we want. We've got security problems, and one that I work on regularly is an interoperability problem. There's a lot of silos out there, so architecturally, we're going to need to address this. No standards, and one of the reasons there's no standards is because of rapid changes. And so the tech ultimately that we're waiting for, this is what I want, I want something that's long range and low power wireless, and it gets decent data rates. We're talking like maybe 600 kilobits per second, and I don't have to pay for it, and it's everywhere at all times. When we have that, I'll be a very happy man. And I'd also like some batteries that have infinite charge cycles, and they hold about 1,000% more than the current models. So if anyone's working on that and has it, please come see me. And our energy harvesting will also help with the battery situation, but it's pretty poor. Solar is okay in sunshiny areas. It can work to power sensors, but we can't harvest from vibration very well or anything yet. Still, thermal's not too bad. And we're looking for security that holds up well in IoT scenarios, but doesn't require absolute geniuses in the company to implement, and that way we can hit scale. And then I've mentioned again the lack of talent in the area. and talent pools are growing. So let's look at the IoT stack, and this technology stack is very similar to anything you might see elsewhere, but there's a couple of tweaks that are in mind that are based on just like what I've experienced in the real world. Obviously, we start at devices at the bottom, and this is everything. This is sensors, this is legacy systems, doesn't matter. And immediately above that is what I call connectivity 1. This type of connectivity is generally not TCP/IP. It's often really constrained. The reason that wireless is the primary mode for the devices is because the devices need to be located in areas where you can't run cables. They move around, they come on and offline, with some regularity. And so your connectivity tends to be low power wireless so that they can work on a battery. And this just does not connect to the rest of our IT infrastructure very well at all. And so immediately above that, we have something to handle it, which is IoT gateways or hubs or base stations. And this is kind of what I would call like the edge hardware layer to be able to handle that type of connectivity 1 problem. And on top of that, we get to edge processing, which that includes edge computing / fog computing. It includes just kind of like scripts that run in a smart gateway. And this is your last opportunity to work with data before it enters the larger system. Then we enter connectivity 2. This is where you tend to leave the building. This is where you tend to go over cellular as your backhaul. It's TCP/IP, and it's pretty well understood. So there's not much need for innovation here, although if someone comes up with something good, I'd love to hear about it. And then we enter into the back-end ingress and the ingestion layer. The reason why we have a real layer here is because you have volumes of data and speeds of data that are just unparalleled compared to prior situations. And so it doesn't have to be a separate piece of software than what else you've got, but you do need to make sure that you look at the scale that it's going to need to handle because it's centralized, and that's very different than on the edge where you can spread out your processing. And so then we get into some kind of central processing. This is such a generic layer, but this would be your business logic, this would be your data analytics, this is all the stuff you do with the data in the back end, and finally we arrive at some kind of application layer where you can make use of all this stuff. Now something to note, which is not often discussed, is on the presentation and application layer, you probably have something making a decision. How do you enact that decision in the real world? Well, this stack, unlike other IT stacks, it goes in 2 directions. And this is a really big challenge from a solution architecture standpoint because now you have to talk about opening up edge scenarios. If I have a warehouse that's just been instrumented with sensors, do I really want that warehouse to have some exposed network ports on the public internet so I can reach it? Probably not. So I would say, oh, I want to keep it on the WAN. Well, there's even problems with that we'll look at. So bidirectional is the name of the game. And this is from a talk I gave over at Amazon. And so the new landscape is, I differentiate between old cloud and new cloud because there's a lot of new cloud infrastructure being stood up to deal with specifically with IoT. That's fine, but it is going to need to integrate eventually with the stuff that's out there that works at large scale and the stuff where there's a lot of value. No one's going to migrate from their existing infrastructure to the new. They're just going to add the new in. And so we have edges and we have devices. And the state of our IoT architecture right now is a little something like this. You've got brand new devices that talk to a brand new cloud. Maybe they talk through a brand new mobile app to reach said brand new cloud. This is just like the bare beginnings, and yet this is most of what we see out there. So the development boards that you can get for IoT that allow you to prototype rapidly and so on, a lot of them talk to some private cloud that the company who makes the boards hosts. And so it makes it look really easy for your prototype IoT board to go and just get connected, and you connect it via Wi-Fi. And you do that by plugging it into your computer, and then you do your programming, right? You flash the board and you give it like the Wi-Fi password, and then the thing connects and you say, this is incredible, I've got an IoT proof of concept that we can run. So then you take it in the warehouse and the Wi-Fi only goes so far past the offices, and then into the deep warehouse you don't have Wi-Fi. So now it breaks down. And if you do have Wi-Fi, then somebody asked the killer question. So that company that makes the board, how do we know that their cloud is compliant for our data, and can we get a private version of it? And it just all starts to fall apart. So prototyping boards are really staying in the prototyping area, and when it comes to enterprise IoT, you really can't use them. You have to think very differently about it. And if we do it right, we start to mix in with some of the old M2M stuff that we've had, which is you have devices within a building or within an edge talking to other devices right there. That's your closed loop opportunities. And we also start to route around the public internet to do inter-edge connections. But ultimately, we want to get to something like this. And so if you were to really abstract out those arrows, it becomes the cloud extending into the edge and vice versa. How do we do this? Because you can't just go and open up public IP addresses everywhere and so on. That's what we're trying to get to. So let's talk about what fog computing really is, and there's so much to be said about it that I'm just going to give you enough that we can start looking at some architectures. But so it's also called edge computing. It doesn't really matter to me. I prefer the term edge, but fog is starting to dominate, mainly because fog, I think, is, it's got a catchiness to it, and it also is just, an edge can mean a lot of things, but fog didn't really have a great definition until now, so I think it's a kind of a namespace that's available. Plus, Cisco spent a lot of money spreading the term fog computing, and you know, that's in play. So I piggybacked on that with naming Eclipse IO Fog. So, so the basic idea is that the cloud is coming down to the ground, and that's what fog is, right? So, although a little bit misleading, because as we'll see in a second, the fog and the cloud are entirely different from an architecture standpoint. But so your whole goal is to get flexible processing in the edge environment, and yet still be able to do remote administration. And so in order to make this possible, you're going to need to have security models built into the fog that you can bank on as a software engineer, or your team can bank on. Because if they're not there and they have to be built in with every application, then you're no better off than flashing boards, right, and just having some kind of a remote update script. And then it needs to have fog services. If if AWS was lacking some basic infrastructure such as S3, right, for file storage and retrieval, if that wasn't there and all you got was just kind of VMs, right, as you spun up a cloud server and you had to write all that, cloud really wouldn't be so much an infrastructure as it would be just kind of a different way of deploying servers dynamically, right? So cloud services exist and fog services exist, and we'll look at them. They're very different. And you can think of fog computing as being almost like a universal runtime or an operating system that you can rely on at the edge. And in fog computing / edge computing, microservices architecture is already dominant. It's not really a question anymore. So if there's a single language plugin or script model, that is going to get you, down the road a little bit. But ultimately, we already know that microservices in the fog is the way that things are going to pan out. So be wary of anything that doesn't talk about that kind of model. And so let's look at why or how fog is different from cloud. So cloud has very stable internet, not just internet, but network connectivity between the elements of the cloud. And it's got a high speed, high bandwidth network. There's physical security. You don't open the doors to your cloud data center, right, and say, just come on in, yeah, it's all good, poke around, it's fine. The physical security is the founding layer of the security that you can trust for the cloud, which is that no one can touch the servers that are running my cloud stuff. No one can touch them except the people that are supposed to. And you don't really care which server stuff runs on in the cloud. You spread it across and you say, this one's running on box 17B. I don't care. I don't even know what that is, right? It runs on something that looks like everything else. We spread load. And to do that, the hardware is pretty homogeneous, not entirely, but you don't have boxes that are just a completely different architecture than others. They're all x86 and 64-bit and so on. And the hardware tends to be pretty capable, and you've got all the electricity you need. So fog is obviously very different in that the connectivity comes and goes. Somebody's on their bicycle and they pass by a point where it can connect, and then they're not connected for the next 20 miles. And the network tends to be very constrained, both in terms of speed and bandwidth. So a really good example of this is, how many people have heard of Sigfox? Do you know this company? Okay, a couple. So I love Sigfox, but you're looking at getting about 20 bytes through in a transmission, and it'll take you about 4 seconds to get it up and 15 seconds to get it back down. So if you want to lock the wheel of something that's being stolen, probably not going to cut it, because 15 seconds is enough time for someone to just roll that right into their truck. So self-locking bicycles should probably have some edge processing going on. So all of your fog, you need to assume, is publicly accessible. So if you put a sensor and then a little fog compute box on the side of a building, it might be above, where people can reach without a ladder, but it is generally publicly accessible. And so if you think about what happens then, if somebody grabs their fog box, do they actually grab a piece of your network? Do they grab the ability to take that home, reconnect it with internet connectivity, and get into your network? And there's a lot of IoT devices that are this way. You think that your home security system, which is connected, is very secure, and maybe it will detect someone intruding, but if somebody manages to nab one of those cameras, they can probably shut down the rest of it unless it's been well protected. And there's been multiple examples of these types of IoT products getting hacked and spoofed and so on. And in the fog, this is actually my favorite difference between cloud and fog. In the cloud, you spread processes around and you don't care where they run. In the fog, you care very much. So if I'm going to run an employee ID detection microservice and I want it to run in the fog right at the entry gate for my, from my manufacturing facility, if I deploy it to the fog and it deploys to the broom closet, I'm going to be pretty upset. I want it to run right at the gate because it's going to pick up the RFID or the Bluetooth low energy signal coming off of the employee ID badges, and therefore it needs to run where I told it to run. So this is just a complete difference from cloud. And if there's like one thing that you think about in the way that you architect edge stuff is that edges are sharp and cloud is fuzzy. And that's just the way that that's going to be. I can't think of any other way to do it, unless you run everything on every fog box, which is really stupid. And so fog stuff tends to be totally heterogeneous. You've got an ARM 64-bit, and then an ARM 32-bit, and then you've got an x86 Intel Atom processor, and so on, and you're trying to mix all these things together. And they don't tend to have a lot of memory, and they don't tend to have a lot of processing power. They're decent, but it's nothing like you'd put in a data center. And sometimes also you have to be very mindful of doing like wireless transmission, because they don't have big enough batteries and they're going to run out of juice. So you say, I can get my data once an hour. And you would need your software to be aware of that. So let's look at some of the fog services. And I'm just going to point out what's in Eclipse IO Fog, because while there are other fog systems that have similar services, some of these are, I think, sorely lacking from some fog systems that are out there. So the primary one is a distributed data bus. And so if you're going to write a microservice for the fog, if you need to know which fog box it's going to run on so you can tweak your code, that's pretty crappy. Because now you're going to write, 15 versions of the same microservice to run in the 15 deploy locations? You should have some abstraction of the flow of information so that the one microservice can look at the data and always looks local to it. And so to implement this, we have a dual mode bus with Eclipse IO Fog. It spools to disk because you might have a power cycle, you might need to query history, but it also does in-memory. And so the in-memory data bus is used to achieve low latency, and we clock at about 15 microseconds of latency at 1 million messages per second. So that's pretty good. Now that's on decently capable hardware. On a little ARM processor, it can't get that good, but it's still good. And so you should also have this transport of information between fog nodes, and nobody should have to employ a network engineer to make it happen. So think about if you had to stand up a VPN between the vehicles that are driving around and the warehouse that they're going and picking stuff up from, and so on, and then you add a new vehicle to the fleet. And so now you got to flash the thing with all the VPN info and so on. And so you have like this endless network engineering effort that goes on in order to interconnect everything. If you're going to dynamically interconnect stuff, then you literally have to have someone on call, right? Where you're like, oh, we just brought online 2 new machines. Can we get you within the next 20 minutes to connect them? We want their data. Something's got to be better than this. And so automatic dynamic interconnect, and that's all part of the distributed data bus, and it has to be super secure. And if you look at, how many people get the Eclipse Foundation newsletter? Cool. It just got published last night, and the primary article on IoT technology in there is this, is the dynamic interconnects and how they're secure for Eclipse IO Fog. So I recommend reading it if you're interested in like, how do we do it? But basically, because we can push code to different things dynamically, we use that to embed security models and push them out at runtime. So there's no way to have prior knowledge of how to do the interconnects. You'd have to be authorized. And so also microservices configuration. So let's say that you write a microservice that passes data up to your AWS instance. that is your main ingestion layer, right, for IoT data. Do you want to write software that embeds the security information, or do you want to have it delivered at runtime? Right? You'd rather, of course, have those secrets delivered at runtime if you're going to have a universally, reusable microservice. Well, so part of the fog should be the ability to deliver dynamic configuration to a microservice and have it be the same for all microservices. That way, there's kind of a standard build. So that's a fog service. And then hardware abstraction. So I think this is one of the most fun things to play with that I have seen in the last year. And we have this thing called REST Blue. And it'll probably become an Eclipse project of its own, because it just should. It's a REST API for Bluetooth Low Energy. And so how about any Bluetooth Low Energy developers in the audience, or has anyone ever even tinkered with BLE, like on an iPhone app or an Android app or something? Anybody built with it? Oh, you guys are in for a treat. You may never know how bad it is. It is pretty tough to work with. It just, the connection drops and you got to go through this whole stack of cycles again and stuff. So we abstract hardware in the fog, and that's so that when you port your fog processing from one fog box to another, one piece of hardware to another, you should be able to access the underlying stuff like the Bluetooth radio without needing to write different code for each of the hardware implementations. And this is in essence why Android and iOS development works, is because they open SDKs for getting the gyroscope, and it doesn't matter if it's an iPhone 4 or an iPhone 6, it all works the same. And so we need that in the fog. Common logging, remote debugging. The remote debugging needs to be a lot better. And I'm even saying that about Eclipse IO Fog. But just in general, when you put stuff out to the field, it's super expensive to go and try to debug it. You got to send a person out there if you can't remotely get access to the data that you need. So how do you attach a debugger and look at what's happening at the edge? It's pretty tough. We've got some of it figured out, but open to suggestions on what would improve that. And also, you should get low latency control signals, like such as you've got new config, or we're about to power cycle use, right? So you're about to restart. You might want to store some of your stuff, or use like the abstracted storage to go and drop something into the fog itself. So there are some key reasons why to use fog computing, and these are going to be the drivers that come from, this determines the budget and so on. But one of the main ones is cost. So if you pay for cellular for your IoT devices, and they're going to take a picture and on the sensor and use it to do visual analysis of the state of degradation of the machinery, right? You take a picture once a day. Well, 1 photo a day, 1 megabyte a day, right? But then do that times 1,000. So you're sending a gig a day over cellular if you've got 1,000 of these sensor nodes out there. Forget about 10,000, right? So the costs start to get astronomical, and you really want to do the processing there on the edge if you can. And when it comes to the WAN, if anyone's done enterprise IT where you've set up WANs between manufacturing facilities or whatever, it's expensive to get it in place, and so you put it in place in order to have like long-term 20-year lifetime connectivity. Are you really going to set up WAN connectivity to something that only gives you incremental value from data? You're probably going to say just skip it, right? We don't need data from that device because it's just too expensive. So you want some other method. You want to take advantage of the public internet, which is essentially everywhere if you can get connectivity to it. And then your hardware choices really open up if you're using fog. You don't have to have a specialty base station or specialty IoT gateway if it's running fog, because you can use software to solve most of the stuff. You can do dumber sensors. So if the sensor has to have Wi-Fi so that it can talk to the cloud in order to get its data off, you have a whole bunch of devices that, although Wi-Fi chips are cheap, right? So now you can do sub $10 for a whole pre-certified Wi-Fi module. You also then have to have a bigger battery, and then somebody has to do the configuration to put it on the Wi-Fi, and otherwise your Wi-Fi has to be open, and so these are, you don't have a lot of good scenarios. So having devices that are a little too smart actually drives up costs and implementation, or I would say like deployment costs. And with fog, you can retain legacy. So if you've got stuff that was never intended to talk to the Internet of Things, you can use software to talk to it, and then the software out the other side talks to the Internet of Things, and you can keep in place stuff that was really expensive that you want to use. Your development costs go down, and then third-party microservices are part of that. If you can, use something someone else built and just deploy that and be safe from having to do custom dev. And performance is also really important. So some of the best round-trip cloud connectivity you can get is with systems like PubNub And the best that they'll give you, I think they're awesome. We even work with them, have integration with them. But the best you can get is 1/4 of a second, and that's guaranteed. You might get 50 milliseconds, but you know, as architects, right, you don't think about what is my best case, I'll plan around that. You think, what is my guarantee? And the guarantee is 1/4 of a second. So in manufacturing, you often need sub-millisecond, and so it's the case for edge computing right there. And so processing very close to the source of data, this is great for security and privacy and stuff too, and you can split the workload logically. It's really easy to take a single stream of data and put it through something the equivalent of like a BeagleBone Black, right, in an industrial environment, massage or manage the data or filter out junk, and then have all of the final data aggregate. That's a lot easier to handle than the pure stuff that comes raw off the machines and hasn't been filtered. So it's another common or main business reason for fog computing is security, privacy, and compliance. And so with the fog, you keep the data where you want it, you do the processing there. In fact, I put this here with the reach into the edge, you can actually keep the data where you want it and go peer into it. Like without moving it to the cloud, you can actually open portals into the edge and go see it without having any kind of edge ports open, right? So it's called a double opt-in method in which both sides opt into the connection and both are outbound connections. So you punch through NATs and firewalls and stuff. And so, and that goes to the second and third point, which is you don't want any open ports on the edge. That's kind of obvious. But I'm actually an advocate for not having any open ports to your data center or your cloud either. And that might sound a little crazy, but really think about it. If you have an IoT data ingestion point that is your, this is where you gather up all of your IoT data across the globe, and this is, you know, like you host it in maybe AWS or something similar. Once it becomes public knowledge that this is the ingestion point, which someone will find it, then it can be denial of service attacked. And you just don't want to have anything open if at all possible, but up until now it's been a little difficult to do that because how can you have connectivity, right? So it would all be WAN based and nothing would use the public internet. You can use the fog to go point to point, and I'll give you an example when I show a fog layout of how to do that. And so you can use software in the fog to add security, and one really exciting thing that we're going to publish maybe in about 60 days with it's a test bed with GE, my startup company IoTrax, Cisco, and Samsung. And we're publishing a paper on how to use the fog to implement novel security models that would be you know, really impossible without the basis of fog computing. So, and it starts with the device. And so another reason for using fog is connectivity. If you don't have a smartphone, then your Bluetooth Low Energy device is completely disconnected from the Internet of Things. And so, I mean, because we all have smartphones in our pockets, our consumer devices generally don't need any different fog, right? An iPhone app and an Android app is good enough fog. But in the industrial or enterprise IoT space, you're not going to use phones to instrument a warehouse, right? You need something very inexpensive and durable that can sit on the warehouse shelves so that it can talk to all of the RFID and Bluetooth Low Energy stuff that's floating around. You just simply can't use a smartphone for it. And you know, you want to talk to things that are on serial and parallel ports, and and protocols become far less important. When you use software to do translation at the edge, you don't care really anymore if one is speaking CoAP and the other is speaking MQTT and the other one is Modbus. It's fine, we can make it all work. And so that leads to the last point, which is finally we can connect devices to each other within the edge environment without having some kind of a central IoT platform in the back end. And you know, there's a ton of IoT platforms out there, and some of them are from very large companies. But the main sticking point with a lot of them is that they're trying to centralize everything so that they can then branch it back down. And you've got the round trip problem, you've got the security problem, and just in general, who's going to write the software in the back end to say, oh, I receive data from 2,400 different device types across the globe, and my job is to normalize everything and make them all look the same? You should probably do that real close to where the device is instead of trying to do it centrally. So as engineers, with the fog, you can write in any language, and you can use skill sets that you already have. So this is probably important if you run a team, because you don't want to train people up on how to write proper C code so that they can flash the firmware in a device and make it work with the cloud. And you can use whatever libraries and frameworks, and you can use one microservice across different fog hardware. And you get a deployment model now for IoT solutions, which is how are you going to update all of the edge processing if it's on specialty gateways? Each gateway is going to have its own version of flashing the binaries that are there, right? And so you might have 15, 20 different companies that you have tooling from. This gets out of hand pretty quick. Well, if fog is done properly, you have one place to go and push new code. And you can push the code kind of in en masse, right? Which is, let me push out to 1,000 fog nodes, all the same updates, and then we'll run some edge tests, and then we'll roll it back if it fails. So, QA in the edge environment is not usually talked about, and that's because we don't yet have deploys to the edge environment that are big enough. But when you think about it, if there's a water valve that is used to do the cooling in a manufacturing facility and you're trying to automate it, and you go ahead and you update a microservice that runs, and maybe the business logic and the edge analytics changes, don't you want to run some QA tests on that, on the actual equipment, on the actual fog node before you decide that it's ready for production? Because otherwise you're operating in a vacuum and then you push it out there and you discover that the valve never closed, and so you actually ruin product and you ruined your manufacturing run. So this is some dangerous stuff. So think about the QA. And so some of our concerns are the location and the condition of data at rest. And the condition, I mean encryption, I also mean normalization. So where are you keeping data at rest, and are you protecting the data in motion? And there's going to be 3-4 disjointed pieces of an IoT solution. So, can you really guarantee that they're protected between the device and the first gateway that takes in the data from the device? And once you go beyond proof of concept, what's the scalability? And then this is actually with some of my customers with the startup, IoTrax. They know that the investment they're doing now is going to be leveraged in another 18 months, another 24 months, to do new things that they can't predict. So is it really IoT infrastructure that's being architected, or is it the backing infrastructure for a single business case? If it only works with a single business case, what are you going to do when you have a great new idea and then you say, well, the thing we have doesn't hold, and we got to scrap it and start over? So there's an emerging title, which is Enterprise IoT Architect. And in that title includes this kind of foreseeing of, well, we're going to want to lean on this stuff more and more with new applications. How do we get the right infrastructure in place? You're going to want to retain your data center investments and break down silos. And this is the interoperability problem. And you want to do end-to-end security if at all possible. It's kind of hard to think about that. And then you want failover and system continuity. So now let's get into a little bit of details on the fog hardware that's possible, show you some contrast, and then I'll show you some solutions, and then we'll have some time for questions. So the smallest thing that can run Eclipse IO Fog is a Raspberry Pi Zero. And they're actually a little hard to get a hold of because they price them at $5 retail. And you'll even find people on eBay selling. They have a new version called the Raspberry Pi Zero W, which has Wi-Fi and Bluetooth Low Energy in it. Actually, it's full Bluetooth. It includes Bluetooth Low Energy, so it's Bluetooth 4. And that one is, you kind of can't get it right now, and there's people on eBay selling them for $100. Those go for $10 retail with the Wi-Fi and stuff, and then $100, and that's because of the short supply. Well, they'll get it up to speed, and you'll be able to get them in large quantities. But so you can typically get about 6 microservices to run on a Raspberry Pi Zero. So for $5, I'd be willing to throw one of these underneath every table in this room if I had a promising business case for running software right there where maybe students were sitting or conference attendees were sitting. Raspberry Pi 3, we often give these out as dev kits, and $35, and you get about 12 microservices out of it. And the Pi 3 has Bluetooth and Wi-Fi, so it's really common. Some people call this a blue box because you just take it and you mount it to the wall, and now you have 30 feet of Bluetooth. And so you can run software against that 30 feet of Bluetooth listening. And there's even a company in the UK that is starting to put not Pi 3s, but equivalent boards in lighting fixtures that they sell. So whenever a light fixture is installed, it doesn't come with IoT fixed hardware like Zigbee or Z-Wave. It comes with generic fog computing, that 64-bit architecture, so you can push code to it, every lighting fixture in the building. And so they're perfect because they're overhead. So you get this range, and you can fix little antennas around the perimeter and stuff. You can get incredible coverage for a hospital, which is a very common use case for Bluetooth Low Energy, by the way, and enterprise IoT is hospital scenarios. So then let's go next step up. I don't like this product. I really don't. It is expensive, and it's not that much better in performance. It has all kinds of radios and stuff in it, and I have spoken to Dell about improving it. So the product manager is aware of what they need to improve. I'm sure I'm not the only one who gave such feedback, but for the cost, the physical form factor is fantastic, and the rest of it is mediocre. Twice the microservices, but 10 times the price. It's terrible. Way more than 10 times the price. Yeah. So next, the comparison to the Dell IoT Gateway is something that has been around a bit longer. AdLink has been doing this for a long time. And so as they graduate from M to M, you might want to look to companies like this. Digi, AdLink, they're doing a great job of taking their M to M hardware and infrastructure and turning it into IoT. So you can get the same 24 microservices on average, and it's only $1,200, but this thing's great. I love this box. And then very common in the back office rack in the building or in the data center, just use a regular Linux server and you can get a ton of processing out of it. On Monday, I did a demonstration here at Eclipse IoT Day, and I brought in a 1U, just a super micro box that costs like $750, and used it to do a demonstration with a camera stream that was right here in the building. And it's amazing what processing you can get out of those with the fog. And so this is a view of the user interface for Eclipse IO Fog called IO authoring. So you've got this thing called the fog controller, and that tells all the fog nodes what to run, what microservices to run on which fog node, and so on. But it has a REST API. And so if you're going to do any work outside of, of programming it, you'd want to use a UI. So we've got this UI that's available. And so what you got here is, this is actually from that demo. So I started with a microservice that was written for the Linksys camera. And this is just an IP network camera. And so it streams the stuff and it makes it available if you want to query it. So this microservice was written in Node.js. And it was written by a third party. And it goes and it takes it queries this camera on the network. The config you give it is what's the MAC address of the camera. And so that way it can go and it can find it on the network for you. Okay, so this microservice is pretty cool. And so it'll go and it'll get, and we're taking a snapshot from the video stream because we're going to pass that over to Google TensorFlow. We made a microservice out of that to tell us what the camera thinks it's seeing in the room. And so normally we would send a megabyte photo up to some cloud and do image recognition. But as I mentioned, if you're going to do 1,000 cameras, you're going to start to accrue some real costs there of data transmission. So do it in the building. And so one more thing I'll mention about that Linksys microservice there. It had a cool feature where you could open a port, which the fog lets you open ports. You could open a port to talk to port 80 inside the microservice, and it would recognize that and send the photo that it had captured out. And then you have this capability with the fog of opening, it's called a public pipe, where you can open a URL on the public internet that allows you to connect directly into the room, directly into that single microservice on port 80. So then I had a URL that you could use on your own phone and look at the camera in the room. And the camera directly sends, through the fog microservice, directly sends the image over a secure pipe to your phone. There is no intermediary, no stops in between, and it routes over the public internet. Very similar to a VPN, but it gets stood up and taken down dynamically. So if you think about this capability and what it causes you to do from an architecture standpoint, you stop thinking about what pipes do I need to put in place and what's their capacity, and you start saying, well, how can I get the best connectivity as a backhaul because I'm going to make use of it for everything in the fog up. And so the TensorFlow is written in Python, of course, because that's a Python-based library. And we held up some photos, and then we said, let's see what this thing says. And we held this up, and it told us that was Granny Smith. And this is all staying in room, which is pretty cool. We held this up, and it told us it was a sorrel, S-O-R-R-E-L, which I didn't know what that was. And that's a chestnut-colored horse. Well, thank goodness, because otherwise that would be pretty bad image recognition. So I learned something from this microservice. We held this up, which is a seahorse, and it got it kind of right. It said an isopod, which is, I think, the family of it. I was pretty impressed, but it did not get seahorse, and it had a whole bunch of other crazy suggestions. And we held this up, and it said a hockey puck and a lot of other stuff, and it just had no idea what to do with it. It was pretty fun. And it's not just photos. We were holding up, somebody did yesterday a water bottle, and then it was like 98% chance that that's a water bottle. So this thing's pretty impressive. So then, but then what do you want to do with it? Well, we go 1 megabyte into the processing in this microservice, and this JSON REST API microservice is in the data center. It's not in the room at all. And what it gets as output from here is it gets the text of what's being seen in the room. So we go from 1 megabyte to 200 bytes. I'm happy to send 200 bytes every 5 seconds. I can handle that. And so I can handle that at a quantity of 1,000, right? So you just get this massive cost and traffic reduction by pushing the edge processing there, but you have a model for doing it that makes more sense. And so then the last one I'll show you here is, we do a lot of demos with this, but also this is great for production releases. So this is a heartbeat monitor that is optical based. You guys have probably seen these ones that you wear across your chest, and some of them even require you to kind of like gel up. You're not going to put those on a patient in a hospital if you can avoid it. But you'd love to get heart rate. So this thing works a lot like the Apple Watch, and you just wear it, and it'll go on the forearm or the upper arm. And the band comes off and can be cleaned. So it's like, this is great for hospitals, because you can take the band off and wash it. And I'm sure if you do a bulk order, they can give you ones with more attractive colors for the hospital. But anyway, so it has no interface other than a button to turn it on. And speaks Bluetooth Low Energy. So what we have here is this is an implementation that used this thing, and this heart rate input is it's the adapter for this piece of hardware. It knows how to speak to it over Bluetooth Low Energy, and we take it and we pipe it out to a JSON REST API in the data center with no patient affiliation, no context, just heart rate. And we do that because what we want there is we wanted to open an API for all of the data scientists at Kaiser Permanente, for example, to be able to look at heart rates across many patients and have that data kind of coming in, streaming, and start to find some correlations. But there's no patient data, just a heart rate. But locally, on-premise, we pipe it into an adapter in the fog that talks to Epic. And so Epic is the world's leading patient record on-premise solution, right? So Epic is this big monster. It's kind of like the SAP of hospital systems. But you do it on-premise and you pipe it over. Now we get patient context, because we've associated some identifier that's built into this. MAC address is typically a good one, but you can also do other things. We've associated with a patient record when we check them in. And now when we gather the heart rate on-premise, we're okay, it's HIPAA compliant still, to merge that data of the heart rate with the patient record. Where do we put it from there? We have a data lake that's on-premise, and we do it with a Hadoop microservice. Each of these can be written in a completely different language, and many of them are. And then let's say that we have a HIPAA-compliant implementation using Force.com, and we pay a lot. You can pipe it from Epic into there and start to reach your broader systems. So that's how you get out of building, is you finally have an adapter that goes to existing backends. So I hope that this gives you some insight into the different ways you can think about leveraging fog and get away from, I guess, the tried and true architectural approaches of saying, well, we're going to spec infrastructure, and then how do we leverage it, and what's our bandwidth constraints over time, and so on. And it starts to get you into a different mode of saying, well, dynamically, what would I allocate there if I had edge processing, and so on. So it looks like we've got, we're at 1 o'clock now. We started late. Feel free to stay for questions, but I figure, if it's lunchtime or whatever, I wouldn't mind if people head out. So I'll hold there. Questions about the presentation? I'll also stick around if anyone wants to do private chats. Yes?
In your earlier slides, you said that all of the data appears to be local.
Yes.
That seems to me to be a little dangerous. That I would want my software to know the difference between local data, which is cheap, and remote data, which is expensive.
That's a very interesting point. So it appears local in terms of the ability to access it, but one of the things that we have a constituent company using Eclipse IOFog has asked for is prioritization and quality of service ratings. Because you're right, this might be data that appears local, but you need to know that this is data that was very expensive to get there, and so you should not go and query a ton of it, for example, right? This is a very good point. That's true too, right, exactly, yes. And you would want to know before you take an action on it, right? And you want to get a high priority delivery of the latest. That's a very good point, very good point. Any other questions? All right, well, thanks everybody. Hope this was an informative talk, and enjoy the rest of your day.